Welcome to Tech Girl Kannada YouTube channel. IoT Sensing and Actuation. Introduction. The basic science of sensing and actuation is based on the purpose of transduction. Transduction is the process of energy conversion from one form to another. A transducer is a physical means of enabling transduction. Transducers take energy in any form: electrical, mechanical, chemical, light, sound, and others, convert it into another, which may be electrical, mechanical, chemical, light, sound, and others. Basic outline of the differences between transducers, sensors, and actuation. Parameters: transducers, sensors, actuators. Definitions: transducers convert energy from one form to another. Sensors converts various forms of energy into electrical signals. Actuators converts electrical signals into various forms of energy, typically mechanical energy. It is an output transducer. Can be used to represent sensor as well as the actuator. Sensors are the input transducer. Actuators are the output transducer. Function: transducers can work as a sensor or an actuator, but not simultaneously. Sensors are used for quantifying environmental stimuli into signals. Actuators used for converting signals into proportional mechanical or electrical outputs. Examples: any sensor or actuator. Humidity sensors, temperature sensors. Anemometer measures flow velocity. Manometer measures fluid pressure. Accelerometer measures the acceleration of the body. Gas sensors measures concentration of specific gas or gases. Others: motors converts electrical energy to rotary motion. Force heads, which impose a force. Pumps, which convert rotary motion of shafts into either pressure or a fluid velocity. For example, in public announcement PA systems, a microphone input converts sound waves into electrical waves, which is amplified by amplifier system. A process. Finally, a loudspeaker output device outputs this into audible sounds by converting the amplified electrical signals back into the sound waves. Above, table 5.1 outlines the basic terminological differences between transducers, sensors, and actuators. Sensors are the devices that can measure or quantify or respond to the ambient changes in their environment or within the intended zone of their deployment. They generate responses to external stimuli or physical phenomena through characterization of the input functions, which are these external stimuli, and their conversion into typical electrical signals. For example, heat is converted into electrical signals in a temperature sensor, or atmospheric pressure is converted into electrical signal in barometer. Figure 5.1 shows the simple outline of the sensing task. Here, a temperature sensor keeps on checking the environment for changes. In the event of the fire, the temperature of the environment goes up, and the temperature sensor notices this change in the temperature of the room, promptly communicates this information to a remote monitor via the processor. Environment event: fire, sensing, temperature sensor, processing, sensor node, monitoring. The outline of the simple sensing operation. Various sensors are classified on the basis of power requirement, sensor output, property to be measured. Power requirement. The way sensors operate decides the power requirement that must be provided for an IoT implementation. Some sensors need to be provided with separate power sources for them function, whereas some sensors do not require any power sensor sources. Depending on the requirement of the power, sensors can be of two types. Active sensors. Active sensors do not require any external circuitry or mechanism to provide it with power. It directly responds to external stimuli from its ambient environment and converts it into the output signal. For example, a photodiode converts light into electrical impulses. Passive sensors require an external mechanism to power them up. The sensor properties are modulated with the sensor's inherent characteristics to generate patterns in the output of the sensor. For example, a thermistor resistance can be detected by applying voltage difference across it or passing a current through it. Output. The output of a sensor helps in deciding the additional components that to be integrated with an IoT node or system. Typically, almost all modern day processors are digital. Digital sensor can be directly integrated to the processors. The integration of analog signal to these digital process or IoT nodes requires additional interferencing mechanisms such as analog or to digital converters, voltage level converter, and others. Sensors are broadly divided into two types of based on their type of output: analog, digital. Analog sensors generate an output signal or voltage which is proportional linearly or non-linearly to the quantity being measured and is continuous in time and amplitude. Physical quantities such as temperature, speed, pressure, displacement, strain, and others are all continuous categorized as analog quantities. Example: thermometer or thermocouple can be used for measuring the temperature of a liquid. Example in all household water heaters. These sensors continuously respond to changes in the temperature of the liquid. Digital. These sensors generate the output of discrete time digital representation. Time or amplitude or both of the quantity being measured in the form of output signals or voltages. Typically, binary output signals in the form of a logic 1 or a logic 0 for on and off, respectively, are associated with digital sensors. The generated discrete non continuous values may be output as a single bit serial transmission, 8 of which combine to produce a single byte output. Parallel transmission in digital sensors. Measured property. The property of the environment being measured by the sensors can be crucial in deciding the number of sensors in an IoT implementation. Some properties to be measured do not show high spatial variations and can be quantified only based on temporal variations in the measured properties, such as ambient temperature, atmospheric pressure, and others. Whereas some properties to be measured show high spatial or as well as temporal variations such as sound, image, and others. Depending on the properties to be measured, sensors can be of two types. Scalar vector. Scalar sensors produce an output proportional to magnitude of the quantity being measured. The output is in the form of signal or a voltage. Example of such measurable physical quantities include color, pressure, temperature, strain, and others. Vector sensors are affected by the magnitude as well as the direction and or orientation of the property they are measuring. For example, an electronic gyroscope, which is commonly found in all modern aircraft, is used for detecting the changes in orientation of the gyroscope with respect to Earth's orientation along all three axes. Here is a functional block of a typical sensor node in IoT. Processor. Sensor, actuator, radio, AC-DC converter power. AC-DC converter power, AC-DC. And the sensor ADC will be having light, temperature, force, position, speed, pressure, chemical. Actuator optional interface, pneumatic, hydraulic, electrical, mechanical. Pneumatic, hydraulic, electrical, mechanical. Radio, Wi-Fi, Bluetooth, Zigbee, LoRa, RFID, NFC, Z-Wave, GSM, 3G, 5G. Figure 5.3 shows some commercially available sensors used for sensing application. Camera sensor, color sensor, compass and barometer. Current sensor, digital temperature and humidity sensor, flame sensor, gas sensor, infrared sensor, rainfall sensor, ultrasonic distance measurement sensor. Sensor characteristics. Sensors can be characterized by their ability to sense the phenomena based on the following three fundamental properties. Sensor resolution. The smallest change in the measurable quantity that the sensor can detect is referred to as resolution of the sensor. For digital sensor, the smallest change in digital output that the sensor is capable of quantifying is its sensor resolution. The more the resolution of the sensor, the more accurate the precision. A sensor's accuracy does not depend upon its resolution. For example, a temperature sensor A can be detected of up to 0.5 degree Celsius changes in temperature, whereas another B can detect up to 0.25 degrees Celsius changes in the temperature. Therefore, the resolution of B sensor is higher than that of the resolution of A. Sensor accuracy. The accuracy of the sensor is the ability of the sensor to measure the environment of the system as close to as its true measure as possible. For example, a weight sensor detects the weight of 100 kg mass as 99.98 kg. We can say that this sensor is 99.98% accurate with an error rate of 0 plus or minus 0.02%. Sensor precision. The principle of repeatability governs the precision of a sensor. Only if upon multiple repetitions the sensor is found to have same error rate can it be deemed as highly precise. For example, consider if the same weight sensor described earlier reports measurement of 98.28 kg, 100.34 kg and 101.11 kg upon 3 repeat measurements of a mass of actual weight of 100 kg. Hence, the sensor precision is not deemed high because of the significant variations in the temporal measurement of the same object under the same conditions. Note, the more the resolution of the sensor, the more accurate is the precision. The sensor's accuracy does not depend upon its resolution. Sensorial deviations. Sensorial deviations are considered as the errors in sensors. The quality of measurement obtained from the sensor is dependent on large number of factors. There are few primary considerations that must be incorporated during the sensing of critical system. Sensitivity error. The sensitivity of the sensor may differ from the value specified for the sensor, which leads to sensitivity error. The derivation is mostly attributed to sensor fabrication errors and its calibration, offset error, or bias. The output of a sensor differ from the actual value to be measured by a constant, hence the sensor is said to have an offset error or bias. Example, while measuring an actual temperature of 0 degrees Celsius, a temperature sensor outputs 1.1 degree Celsius. Every time, in this case, the sensor is said to have an offset error or bias of 1.1 degree Celsius. Nonlinear behavior is a sensor's transfer function deviates from a straight line transfer function It is referred to as its non-linearity. Drift. The output signal of a sensor changes slowly and independent of the measured property. This behavior of the sensor's output is termed as drift. Hysteresis error. If a sensor's output deviates due to deviations in the sensor's previous input value, it is referred to as a hysteresis error. The present output of the sensor depends on the past input values provided to the sensor. Hysteresis can be observed in analog sensor, magnetic sensors, and during heating of metal strip. Quantization error. The error can be defined as the difference between the actual analog signal and its closest digital approximation during the sampling stage of the analog to digital conversion. Aliasing errors. The dynamic error caused by the mishandling of the sampling frequencies leads to the aliasing errors. Now, the sensing types. Sensing can be broadly divided into four different categories based on the nature of the environment being censored and the physical sensors being used to do so. Scalar sensing, multimedia sensing, hybrid sensing, virtual sensing. Scalar sensing. Scalar sensing encompasses of the sensing of features that can be quantified simply by measuring changes in the amplitude of the measured values with respect to time. Example: ambient temperature, current, atmospheric pressure, rainfall, light, humidity, flux. Sensors used for measuring these scalar quantities are referred to as the scalar sensors that act as the known as scalar sensing. Refer the figure 5.3 for example of scalar sensors. A simple scalar temperature. Scalar sensing environment event is fire happening, so the sensing is temperature sensor. This is scalar sensing. Multimedia sensing event surveillance environment and sensing camera sensor multimedia sensing. Hybrid sensing event wildlife mon environment sensing camera sensor plus temperature sensor. Virtual sensing environment S1 S3 and what is S2 E2 happening. Sensing. Different sensing types commonly encountered in IoT. Multimedia sensing. Multimedia sensing encompasses the sensing of features that have a spatial variance property associated with the property of temporal variance. They are used for capturing changes in the amplitude of the quantifiable property concerning space, spatial, as well as time, temporal. Example: images, direction, flow, speed, acceleration, sound, force, mass, energy, momentum have both direction as well as magnitude. They might have different values in different directions of same working condition at the same time. The sensors used for measuring these quantities are known as vector sensors. Figures 5.3a, 5.3c are vector sensors. Simple camera-based multimedia sensing using surveillance as an example is shown in the figure 5.4. Hybrid sensing. The act of using scalar as well as multimedia sensing at the same time is referred to as hybrid sensing. In the sensors, it is necessary to measure vector as well as the scalar properties of an environment at the same time. For example, in the agricultural field, it is required to measure the soil conditions at regular intervals of time to determine plant health. Sensors such as soil moisture and soil temperature are deployed underground to estimate the soil's water retention capacity, and the moisture being held by the soil or not. There may be a host of other factors besides water availability which may affect the plant's health. The additional inclusion of a camera sensor with the plant may be able to determine the actual condition of the plant by additionally determining the color of leaves. The aggregate information from soil moisture, soil temperature, and the camera sensor will be able to collectively determine a plant's health at any instant of time. Other examples are smart parking systems, traffic management systems, and figure 5.4 shows the example of hybrid sensing where a camera and a temperature sensor are collectively used to detect and confirm forest fires during the wildlife monitoring. Virtual sensing in agriculture domain, there is a need for very dense and large scale deployment of the sensor nodes spread over a large area of monitoring of parameters like measuring the soil moisture, soil temperature, and water level. For example, if the data from A's field is digitalized using the IoT infrastructure, and this will advises him regarding the appropriate watering, fertilizing, and pesticide regimen of the crops. This advisory can also be used by B for maintaining his crops. In short, A's sensors are being used for actual measurement of parameters, whereas virtual data, which does not have actual physical sensors but uses extrapolation based measurements, is being used for advising B. This is a virtual sensing paradigm. 5.4D shows an example of virtual sensing. 5.6 Sensing considerations. The following major factors influence the choice of sensors in IoT based sensing solutions. Sensing range. The sensing range of a sensor node defines the detection fidelity of that node. Typical approaches to optimize the sensing range in deployments include fixed K coverage and the dynamic K coverage. The lifelong fixed K coverage tends to assure in redundancy as it requires a large number of sensor nodes. A sensing range of some of which may also overlap. In contrast, dynamic K coverage incorporates mobile sensor nodes post detection of an event, which however is a costly solution and need not be deployable in all operational area and terrains. The sensing range of a sensor may also be used to signify the upper and lower bounds of a sensor's measurement range. For example, a proximity sensor has a typical sensing range of couple of meters. In contrast, a camera has sensing range varying between tens of meters to hundreds of meters. As the complexity of the sensor is in sensing range goes up, its cost significantly increases. Accuracy and precision. The accuracy and precision of the measurements provided by a sensor are critical in deciding the operations of specific functional processes. Typically off the shelf, consumer sensors are low on requirements and often very cheap. Their performance is limited to regular application domains. For example, a standard temperature sensor can be easily integrated with conventional components of hobby projects and day-to-day applications, but it is not suitable for industrial process. The industrial sensors have very high accuracy and precision score even under harsh operating conditions. Energy The energy consumed by a sensing solution is crucial to determine the lifetime of the solution. and the esteemed cost of its deployment. If the sensor or the sensor node is so energy inefficient that it requires replenishment of its energy sources quite frequently, the effort in maintaining the solution and its cost goes up, where its deployment feasibility gets down. Device size. Modern day IoT applications have a wide penetration in all domains of life. Larger the size of the sensor node, larger is the obstruction caused by it. Higher its cost, energy requirements, and lesser is its demand for the bulk of appliances. Consider a simple human activity detector. If the detection unit is too large to be carried or too bulk to cause hindrance to regular normal movements, the demand for the solution would be low. It is because of this that onset of wearables took off so strongly. The wearable sensors are highly energy efficient, small in size, and almost part of wearers' regular wardrobe. Actuators. Actuators. An actuator can be considered as a machine or a systems component that can affect the movement or a control of system. Control systems affects changes to the environment or property they're controlling through actuators. The system activities and the actuators through a control signal which may be digital or analog. The response from the actuator which is in the form of some form of mechanical motion. The control system of an actuator can be mechanical or electronic system. A software-based system, example, an autonomous car control system, a human or any other input. Figure 5.5 shows the outline of the simple actuation system. The remote user sends commands to the processor. The processor instructs a motor controlled robotic arm to perform the commanded tasks accordingly. The processor is primarily responsible for converting the human commands into sequential machine language command sequences, which enables the robot to move. The robotic arm finally moves the designated boxes, which visits assigned task. Monitoring, processing, actuation, environment. Monitoring, processing, actuation, environment. Monitoring by monitor and processing by sensor node, actuating motor driven mechanism, environment, factory automation. The outline of a simple actuation mechanism. Then actuator types. Actuators can be divided into 7 classes: hydraulic, pneumatic, electrical, thermal or magnetic, mechanical, soft, shape, memory, polymers. Hydraulic, pneumatic, electrical, thermal or magnetic, mechanical, soft, shape, memory, polymers. Show some of the commonly used architecture in IoT applications. Brushless DC motor, stepper motor, generated stepper motor, DC motor, relay array, hydroelectric generator, solenoid based flow valve, DP/DT switch, push button switch. Some commonly commercially available actuators used for IoT based control application. Hydraulic actuators. A hydraulic actuator works on the principle of compression and decompression of the fluids. These actuators facilitate the mechanical tasks such as lifting loads through the use of hydraulic power, derived from fluids and cylinders or fluid motors. The mechanical motion applied to the hydraulic actuator is converted to either linear or rotary or oscillatory motion. Pneumatic actuator. A pneumatic actuator works on the principle of compression and decompression of gases. These actuators use a vacuum or compressed air at high pressure and convert it into either linear or rotary motion. Pneumatic rack and pinion actuators are commonly used for valve control of water pipes. Pneumatic actuators are considered as a compliant systems. Electric actuators. They are used to power an electric actuator by generating mechanical torque. This generated torque is translated into motion of its motor shaft or for switching. For example, actuating equipments such as solenoid valves control the flow of water in pipes in response to electrical signals. This class of actuators is considered one of the cheapest, cleanest, speedy actuator types of available. 5.6 A, B, C, D, E, F, I, J show some of the commonly used electrical actuators. Thermal or magnetic actuators. The use of thermal or magnetic is used for powering this class of actuators. These actuators have a very high power density and are typically compact, lightweight, and economical. Example of thermal actuators: shape memory materials such as shape memory alloys. These actuators do not require electricity for actuation. They are not affected by vibration and can work with liquid or gases. Magnetic shape memory alloys are a type of magnetic actuators. Mechanical actuators. In mechanical actuation, the rotary motion of actuator is converted into linear motion to execute some moment. The use of gas, rails, pulleys, chains, and other devices are necessary for these actuators to operate. These actuators can be easily used to convention with pneumatic, hydraulic, and electric actuators. They can also work in a standalone mode. For example, of a mechanical actuator is a rack and pinion mechanism. GHK, and this one shows some of the commonly available mechanical actuators. The hydraulic generator shown in G and H convert the water flow induced rotary motion of the turbine into electrical energy. Similarly, the mechanical switches shown in K and L uses the mechanical motion of the switch to switch on or off an electrical circuit. Soft actuators. Soft actuators, example polymer base, consist of elastomeric polymers that are used as embedded fixtures in flexible materials such as cloth, paper, fiber, particles. The conversion of molecular level microscopic changes in tangible microscopic deformations is the primary working of principle of these classes. Shape memory polymers SMP are considered as smart materials that respond to some external stimuli by changing their shape and then revert to their original shape once the affecting stimulus is removed. Features such as high strain recovery, biocompatibility, low density, biodegradability have been designed to respond to a wide range of stimuli such as pH changes, heat differentials, light intensity, and frequency changes, magnetic changes. Actuator characteristics. The choice or selection of actuators is crucial in IoT deployment. Actuators perform the physically heavier tasks in an IoT deployment, tasks which require moving or changing the orientation of the physical objects, changing the state of the objects, and other such activities. Weight. The physical weight of actuators limits its application scope. For example, the use of heavier actuators is generally preferred for industrial application and applications requiring no mobility. For the IoT deployment, in contrast, lightweight actuators typically find common usage in portable system and vehicles, drones, and home IoT applications. Power rating, this helps in deciding the nature of the application with which an actuator can be associated. The power rating defines the minimum and maximum operating power an actuator can safely withstand without damage to itself. Torque to weight ratio. The ratio of torque to weight of the moving part of an instrument or device is referred to as the torque to weight ratio. This indicates the sensitivity of the actuator. Higher is the weight of the moving part, lower will be the torque to weight ratio. For a given power, stiffness and compliance. The resistance of a material against deformation is known as its stiffness, whereas compliance of a material is opposite to the stiffness. Stiffness can be directly related to the modulus of elasticity of that material. Stiff systems are considered more accurate than compliant system as they have a faster response to the change in load applied to it. For example, hydraulic systems are considered as stiff and non-compliant, whereas pneumatic systems are considered as compliant. Thank you for watching. Do like, share, and subscribe to my channel.